Example, at a distance of 12,000 feet from the launch site, a spectator is watching a rocket being launched vertically. What is the speed of the rocket at the instant when the distance of the rocket to the spectator is 13,000 feet and is increasing at 480 feet per second? Following the guide to solving related rate problems, let's begin by drawing a diagram and labeling variable quantities. We've got the spectator, excuse my drawing, and a launch site, and the spectator is standing 12,000 feet from there. The rocket's going to go straight up, so we'll do a little square at the corner to indicate we're looking at a right angle. The distance from the spectator to the rocket looks like the hypotenuse of the right triangle, and that's 13,000 feet. Let's label the horizontal distance x, the vertical distance y. This is where the rocket is, the very tip, and the hypotenuse distance z. The question is, what is the speed of the rocket at the instant? And the rocket is moving vertically, so what we're after is the vertical distance dy with respect to time dt. That's our diagram. Now let's write down our given values. The hypotenuse distance is 13,000. dz dt, and that distance is increasing at a rate of 480. The x distance, where the guy is standing, is 12,000 feet, and he is not moving. So the change of his position with respect to time is 0. What we are looking for is dy dt, so that's our question mark. And let's go ahead and use whatever information we've got to solve for y. We have a right triangle, so to get the value of y, we'll use x squared plus y squared is equal to z squared. Algebraically solving for y, that's the square root of z squared minus x squared. That would be the square root of 13,000 squared minus 12,000 squared, and solving for y, that is 5,000. So now we also have the value for y. The next step in our guide to solving related rates problems is to find or construct an equation, and that turns out to be the x squared plus y squared equals z squared. We're working with the right triangle. Now we can implicitly differentiate with respect to t. That is, we'll do d dt of x squared plus d dt of y squared equals d dt of z squared. The derivative, 2x, then dx with respect to t, dt. Y squared derivative would be 2y, and with respect to t would be dy dt. And the derivative of z squared with respect to t would be 2z dz dt. We are solving for dy dt, and let's observe that since dx dt equals 0, that term 2x times dx dt goes away. Continuing to solve, 2y dy dt is equal to 2z dz dt. The common factor of 2, we divide out. Now let's solve for dy dt. So dy dt is z divided by y dz dt. The final step is to look at our implicit differentiation. Dy dt is equal to z divided by y dz dt, and replace it with the correct values. Z is given in the statement of the problem as 13,000. We solve for y, 5,000. dz dt is given in the statement of the problem as 480. Solving this, we get that dy dt, that is the rate at which the rocket is getting further away from the spectator at this particular instant, is 1,248 feet per second.